Okay, so welcome to the last session of the second day of QPL. So we have 6 short talks, and the first one is given by Philip. Please.
Hi. This works. Yeah. So I'm going to talk to you about the lambda calculus today, which was designed to be a language for dagger compact categories. I'm going to start by giving you a non-technical introduction and an intuition into the motivation, and then I'll gradually go more technical. So the idea was, and I'm going to explain why I was motivated in higher order stuff. I was looking at teleportation, and I was thinking, this is a picture of the yanking rule that I've seen many times in Bob's talks, and I was thinking that the concept of teleportation should really be the same, regardless of whether you're teleporting just a simple state or whether you're teleporting an entire function. But the more complex the thing you're teleporting, usually the more complex the diagram you're using or the statement in whatever language. So going extremely non-technical now, when you're browsing through your files in your machine, you might have a folder, and it might be called My Files, and this is a typical user interface thing, and you might click on the plus, on the little plus, and it expands into My Papers, for example, and My Music. So similarly, the thing I thought is, you could have a wire which corresponds to a function f, but really this should be expandable into an input A and an output B for the function. So that's just purely intuitive. Let me go on into describing the language, which is the dagger lambda calculus. The language consists of terms. Now a term can either be a variable would be something like x or y or z. It can be a constant, for example c. It can be a tensor of 2 terms, or it can be a term that is starred, like f star, or for example p1, p2, and everything is starred. Now every term has a type. A type can either be an atomic type, like A, B, C, something like that, or it can be a tensor of types, like A tensor B, or it can be a star of the type. So, actually this is meant to be an upper star. So, A tensor B and everything starred, or maybe it can be A star, was tensored. So you can have combinations like that. Now you've noticed that I've used the star. The star corresponds to a form of linear negation. So I'm going to talk a little bit about that linear negation. It's involutive, so A star star is A, both for the terms and for the types. And then the question is, we've seen in many quantum logics that tensor is equal to par. Is it equal to par in this case? And I'm going to say almost. I use a planar negation. So A tensor B and everything star gives you B star tensor A star. And that's to allow for a better, more planar representation when you're if you want to use these things to draw a diagram. Similarly for the types. Now, the language also has what we call the soup, which is a connection between terms of the same type. And these connections, well, the soup is a set of connections. And these connections essentially correspond to connections between wires in a categorical diagrammatic sort of way. So I have a picture here to illustrate this. You can see that the first wire is connected to the second one, as in this one connects to this one. And then we have a function f, which is here, and the second wire goes in as an input, and then from the output of the function is connected to the third wire, which is then wired to the fourth wire. So that's a rough way of describing an example. So I found a nice picture of a switchboard. In some ways, this is a little bit like the old telephone switchboards that we had, where we could connect one person's telephone to the other by connecting the wires. So what does a sequence in the language look like? You can have a term and its type, and another term and its type, and a bunch of terms and their types. Then you have a term style. Then you have a soup, which is it's a set like this one. And then you have another term and its type. And that's what the sequence look like. Now, those are the primitives we need, but we can use them to reconstruct lambda abstraction, because we have essentially defined more primitive notions. So we can say that lambda of A dot B is A star tensor B, and similarly for the types, we can say that A lollipop B is A star tensor B. Okay? Now, with that in mind, you can just start using lambdas in just like people do in the lambda calculus. Now, I've designed a more complicated diagram to illustrate things. And from that, you can see that what we really care regarding the left of the turnstile and the right of the turnstile is that on the left, so a sequence will essentially correspond to an entire diagram. And so on the left, you have the inputs. And you have an input of type A and an input of type C. And then on the right, you have the outputs. So you have an output of type D and an output of type E that are tensored. And then the soup is where all the meaty stuff goes on. So if you look at it, you have a function f, which is wired so that A and B star go in as inputs, and D comes out as an output. And then you also have a function G where B and C go in as inputs, and E comes out as an output. So the soup is used to express where most of the computational things take place. There are a bunch of sequence rules in the language. Some of these are very common in many linear type lambda calculus, so this rule and this rule and this rule. Also, the exchange rule is fairly typical, and these two. I'm going to focus on the cut rule, which, as you can see, you're having a sequence which produces something with an output of A, and you have another sequence which, among others, has an input of A, and then when you cut them, this wire and this wire become connected in the soup. So that's what the cut rule does. It connects wires in the soup. This is a carrying rule. fact that it has two lines means that it's reversible. So you can go from something of this form to something of this form, or you can also go backwards. And then there's a negation rule, which applies star on this, star on that, and also on the soup. So using these things, using these rules, we can actually prove, we can actually admit a new rule, which is called the dagger flip, and this is very unique, which says that if you have something that goes from A to B with a soup of S, then you can just flip this, and this is equivalent to the action of the dagger functor, and end up with something that goes from B to A as the soup negated. And this can actually be proved like this, but it cannot be found in paper. There are some soup propagation rules. The first one is called bifactoriality, because it really breaks up the tensor into two things. The next one is called thread. It's just there to handle the case where you're hardwiring something to itself. And this is just for the identity, cancelling things out. And there's also a consumption rule, which says that if you have a soup connection like that, EU, then if U has no constants, then you can go and you can substitute. You can basically go and put a T wherever there's a U in your entire sequence. So the binding here is global in scope. It affects the entire sequence. It's not limited to a single term as it is in the normal lambda calculus. And similarly, if T has no constants, you could have substituted the other way around and gone ahead and put a U wherever there was a T. If neither of them has a constant, you can go either way, and as you'll be able to see in the paper, it doesn't really matter, because the two things that you'll end up with are alpha equivalent. There's a way of defining application based on these things. And it's basically a shorthand for a variable x and a connection in the soup. Now, the lambda calculus has a number of nice properties that are proved. For subject to traction and consistency. It's also strongly normalizing and confluent. And going back to the Howard-Lambda correspondence, which is the correspondence between categorical quantum logics and dagger compact categories, I'm coming in to fill in this gap of the third thing missing from the triangle. That's the dagger lambda calculus. And what I actually prove is that it's an internal language for dagger compact categories. Now, in terms of future work, there are a number of things to be done. I want to extend this to cover the classical structures, the complementary classical structures, and dualizers as well. I want to have some support for non-determinacy of measurements, and eventually I want to be able to higher order representation for measurement-based quantum computation. Thanks for all this, at least to these people, and many others with whom I've discussed in these past few years. That's all.
Questions, comments, please? So what is dA in your rule for trace?
Yes, I didn't include it in the slides because I wanted to save space. But it's the dimension of A. So it's defined as the thing that you have for every type. So for every type A, that type has a dimension, and it's written as dA.
Thank you.
Anything else? Oh, I have one. Yeah, go on.
The same question, just to make sure that's understood correct. So this dimension is what you think from the compact structure by
Yeah, if you have something like that.
the swap,
If you have a cup and a cap
yes.
that are of the same type, and you
You put the swap in between, and this is the dimension.
don't really need this one. Yeah, you need this one. Yeah, it's that thing.
This is more like a comment rather than a question, but in comparison with, because people use linear logical proof nets also for quantum computation,
Yeah.
but then, so from this programming perspective, your calculus looks to me somewhat you can also do meta programming. So like you take a program and then you take a dagger of it or a negation of it, then you can reverse it. It's so it's nice.
Thank you.
Anything else? Okay. So the next speaker will be Akihito